Hello everyone, I hope you are doing fine. Okay, let's try to make progress in our soil mechanics class. Okay, so you can find French version of this video as well if you want en français. Si vous voulez la version en français, vous pouvez avoir un lien dans les commentaires de la vidéo sur YouTube. Okay, yeah. So we are still on the chapter 4, the plasticity and structure of soil. Okay. So in this chapter, I think the previous video, we have talked about all these points, introduction to liquid limit, plastic limit. And in this video, we will talk about this shrinkage limit. Okay. So I think in the next video, we will talk about these 2 points. In this video, we will talk about shrinkage limit only. Okay. So what is shrinkage limit? You remember this figure? We have used it in the 2 previous video as well. So in this figure, we can see the definition of all the limits, liquid limit, plastic limit, and shrinkage limit. Okay, we have explained the definition of these limits before in the previous videos. Okay, so in this video, we will talk about this case, the shrinkage limit one. I hope you know already what is liquid limit, what is plastic limit. If you don't know, I recommend you see the 2 previous video on my YouTube channel. Okay, so what is shrinkage limit? Why do we need shrinkage limit? The thing is, when soil is humid, then there is a lot of water in soil, and the soil is humid. When the moisture is decreasing, the amount of moisture in the soil is decreasing, soil is contracting. So soil contracts as moisture diminishes. So when this is like when you have a sample of soil, and that soil is humid, there is water inside. If you leave this sample of soil, for example, under maybe sunlight, maybe the water will evaporate. Okay, so during evaporation, the soil will lose its humidity. Okay, so when it will reach a certain point where the moisture loss stabilize. It stabilizes, and favor loss won't change the volume of your soil. Okay, and that mark the shrinkage limit. Okay, it's something like that. We can explain this with this figure. The moisture content in horizontal axis and the volume of the soil vertical axis. Initially, you are here with initial volume, initial water content, or again, moisture content, and initial volume. And if the water in the soil decreases, the amount of water in the soil decreases, the volume is also decreasing. That's the meaning of shrinkage, actually. It means your soil is shrinking when the amount of water is reducing. Okay, then at a certain moment you will be here, here, and here. And finally, when you will reach this point, despite the moisture content is decreasing, the volume of the soil remain constant. Once you reach that point, you have reached the shrinkage limit. Yeah. So from here, to here, the volume will decrease, the volume of the soil, like the soil is shrinking. It was this size and it shrinks when the amount, the volume, the final volume is reached. No matter the amount of water the soil is losing, its volume doesn't change. That's the shrinkage limit. This is the definition actually of shrinkage limit. Okay, so our topic today is about this. How do we calculate shrinkage limit? How do we do experiment for shrinkage limit? Yeah, this kind of thing. Okay, so I will keep this figure here because all along this video we will talk about this figure, so it will help us to for illustration, you know. So, and also I will be keeping some formula around here. Once we establish a formula, I will keep that formula here around here. Okay, the American standard, American standard, the shrinkage limits test with designation D420 and 27. These shrinkage limit tests are done with a dish, a porcelain dish with dimension 44 millimeter diameter and 12.7 millimeter height. Okay, so this is coated with petroleum jelly. It's something like this. You see this dish. This dish is has this dimension 44 millimeter of diameter, 12.7 millimeter of height. Okay, and we inside we coat it with petroleum jelly. This is the American standard designation D427. Okay, so how it works exactly? We put wet soil like this. We fill the dish with wet soil, and of course we make sure that it flat. Okay, so that's why it's saying excess is removed. So the wet soil mass is measured. It means you will go to weight the soil to see how many grams it will be. Okay, and after that you put it, you dry it, oven dry. Okay, after drying you will obtain something like this. See, this is wet, this is dry. Then the dry soil, you carry it and put it in what they call mercury displacement. There is a device in which there is mercury, and the displacement of this mercury will give you the volume of this dry soil. Now remember that the volume of the dish is known already, so that volume of the dish is considered as the volume of the initial volume of the soil when the soil was wet. And after drying, we go to find the volume of the dry soil now. So we just remove the soil and put it in mercury, and mercury displacement gauges the volume of the dry soil. It's something like this. This drawing is showing how the mercury displacement test is done. You see here, this is the soil sample. Okay, so after putting the soil, the dry soil in the mercury, we will have overflow here, and it will drop these sides. Okay, and you can then know the amount of mercury displaced by the soil, by the dry soil, and by measuring the volume of this displayed mercury, you can get the volume of the soil. It's very simple like this. Then if we have the mass and the volume of the soil, initial mass and initial volume, final mass and final volume. We can go for how to estimate the shrinkage limit. Okay, so according to this figure, the shrinkage limit can be obtained by this formula. Omega I minus delta omega. So shrinkage limit, SL, shrinkage limit. This one, omega I, is just the initial moisture content. The moisture content at the beginning when the soil was wet. Okay. And then the delta omega, this one, is the change in moisture content, the water content from here to here, the amount that is changed. Okay. So if you have at the beginning, it's like you have something like this, the amount is here. And if you do minus this distance, you see omega or Wi minus this distance, which equivalent of this distance. You will get this shrinkage limit. That's simple, right? So we know also that the water content or moisture content can be obtained by this formula. Okay, M1 minus M2, and we divide by M2. Of course, multiplying by 100, that is to get it in percentage. Okay, what is M1? Is the mass of the wet soil in the dish. That the mass at the beginning, and M2 is the mass at the end, mass of the dry soil. Okay, so if you remember this formula, we have talked about this formula maybe in chapter 2 or chapter 3, maybe chapter 3. The formula of moisture content or water content, which is weight of water divided by weight of the solid soil. Okay, WS, the solid part of the soil, soil particle. And you can also obtain the water content using also the mass. Instead of weight, you can use mass also. That will be mass of water divided by mass of solid particle of the soil. Okay, and multiplying by 100 to get it in percentage. So here we just use this last formula. Water content is what mass of water divided mass of the solid soil, solid part of soil. Okay, so how do you obtain the mass of water? That is very simple. This is illustration again of the test. This is the dish, and this is the soil. Initially, we have VI. This is the initial volume and initial mass. Okay, at the end, you see the soil has shrinked, so the volume has reduced. We have final volume VF, and the soil mass M2 is the mass of the dry soil. Okay, so by doing M1 minus M2, we will get the mass of the water, right? Very simple, because here the mass M1 here is mass of both soil and water. Okay, so here, since here it is dry, it means there is no water, it's only soil. So if we do M1 minus M2, what we are getting is the mass of the water. That's why we have here M1 minus M2, the mass of water. And M2 is the mass of soil, MS. M2 is equivalent to MS, because here M2 is only soil and the solid soil, the solid part of the soil. Okay, so I hope you understand this formula. Anyway, this is the formula we do that gives us this one, the initial water content, okay, or moisture content. So we will keep this formula just here, okay, the two formula, okay, and keep this also here, keep, because we will use it. So after establishing a formula, we will keep it around here, okay, because we will need to use this formula later to make it easy for you to understand. Yeah. What do we have again? Now we will attack this one, this delta omega. For this one, can be obtained with this formula. How about this one, this part, the variation of the water content? So according to this same figure, we can say, and logically, the variation of the water content, because that is the meaning actually, the delta omega, delta W, if you want, is just the variation of water content. How do we obtain that? You just take V1, Vi, the initial volume, minus the final volume. If you do that, what will you get? If you do initial volume minus final volume, what you are getting is the volume change, actually, the variation of volume. And it just the volume of water, actually, the total volume of water, actually. I'm not sure you understand that, because as I explained already, the same way we did M1 minus M2 to obtain the mass of the water by doing V1 minus V2, Vi minus Vf, will obtain somehow the volume of the water, okay? And by doing so, just agree that Vi minus Vf is equivalent to the volume of the water, the amount of water in the soil at the beginning of the experiment, of the test, okay? Yes. So by multiplying this volume with the density of the water, you will obtain the mass of the water also, somehow. So anyway, I will bring up another formula we have talked about before also. So Vi is initial volume of the wet soil, Vf volume of oven-dried soil, and rho is density of the water, okay? So do you remember this formula also? We talked about this formula in chapter number 2 maybe, or number 3, I don't remember exactly. But anyway, normally this formula everyone knows. Rho, density, is equal to mass divided by volume, okay? So if you do density multiplied by volume, you get mass. This is what we did here. So look like by taking the density of water, we are considering that this is just volume of water. Maybe technically not 100% true, but anyway, by doing that divided by this, we obtain delta omega, the variation of the water content. And then finally, we can combine this. We can use this equation, number 10, number 11, and number 12, and we can get this shrinkage limit formula, okay? This shrinkage limit formula, if you see, if you look closely, this part is just this one. It means we replace the initial water content by its formula, okay? And the variation of water content is replaced by this formula. That is what we have here. Very simply. Okay, we will keep this formula also because we will use it later. So I will put it here. This is the formula for shrinkage limit we have for now. So we'll keep this here and also this figure. Okay, so let's continue. Shrinkage limit. The thing is, this method of doing the test of shrinkage limit is no longer in use according to the American standard. This in 2000, I think they stopped using it in 2008. From 2010, there is another way to do it. The old designation D420 has been withdrawn. So the new one is D4943, this one. Okay, so in this method, in this designation, the method where the volume, the initial volume, is determined by filling the shrinkage limit dish with water. Okay, so you can change. I think with this test, you can do the shrinkage limit test with any dish. But anyway, it's better if you want to buy, of course, for this for your lab, you can. There are a lot of website where you can get this equipment to buy. Okay. So the volume, to determine the initial volume, the dish is filled with water, and the volume of that water is the initial volume actually, because it doesn't matter if it's filled of water or filled of soil, the volume remains the same volume. But if it is not the standard size that we talked about before at the beginning of this video, it doesn't matter, I think. So in that case, the volume, the initial volume, is just like mass of water, the water you need to fill the dish. Okay, that mass divided by the density of water. It means that any dish you are using for doing the test, it doesn't matter if maybe you can use even any dish from your kitchen. I'm not sure. If you are using that and you are not sure about the capacity, the volume of the dish, you fill it water, you weight the water, okay? And by dividing that mass, the mass of the water, with divided by density of water, you obtain the volume of that one. And this also coming from this formula, okay? Volume can be obtained by taking mass and dividing it by density. Okay, anyway, so this is how you can obtain the initial volume. That one is easy. The final volume is quite difficult procedure. In order to obtain the final volume, the VF, the dry soil is immersed in melted pot of wax and cold. After melting in wax, it is cooled down. Then the mass of the dry soil and the wax, both together, is determined in air, and after that in water, submerged in water. Then with M5 being the mass of displaced and the water displaced by the dry soil and the wax, if you take M3, mass of dry soil and wax, minus in air, mass of the dry soil and wax in air and minus the mass of dry soil and wax in water, you will obtain the mass of water displayed by the dry soil and wax. We keep this formula also here. This is how we obtain, you remember, how we obtain the mass of the displayed water, the water that is, instead of using mercury, this new test doesn't use mercury. They are using wax, and the wax around the soil is weighted in air and in water. Okay, by doing the mass in air minus the mass in water, you obtain the mass of water displayed displaced by the dry soil and the wax. So now the volume of the dry soil and the dry soil part and the wax can be calculated by using this formula. This volume include both the soil, the dry soil, and the wax. So by taking this, the mass, this M5 also mass of both, the mass divided by gamma and by density of water, because this mass is supposed to be the mass of not mass of both, but mass of the displaced water, the mass of water. So mass of water divided by density of water, you obtain volume. This is coming from here also, from this formula. Okay, mass divided by density, you get volume. From this formula, you can obtain that. So we know the mass of the water, the displaced water, the water that is displaced by both the wax and the dry soil. Now we go for the mass. The mass of the wax that is coating the dry soil, because we need to remove that mass to obtain the mass of this dry soil. You need only the mass of the dry soil. Okay, so the mass of this wax is obtained by using this formula, because we know that M3 is the mass of the dry soil and the wax, both of them. So if we minus the mass of this dry soil, because M2 is mass of dry soil from the beginning, we will get M6, which is mass of the wax that is coating the dry soil. So after that, we go for the volume of that same wax coating the soil, VWX. So that volume is obtained by using the mass of the wax divided by specific gravity, multiplying it by, which is multiplied by the density of water. This is how we obtain the mass of the wax. So if we have this now, finally, we can obtain the final volume. It's tough, eh? I understand. If you don't, it's complicated for you. That the new testing method is more complicated than the previous one, right? But this is how it works. So the finally, the volume of dry soil part can be obtained by using this formula. The final volume is the volume of the both wax and soil, dry soil, minus the volume of the wax. This volume we have here, this is volume of both wax and dry soil. Okay, if we take that volume minus the volume of the wax we obtain here, we will obtain the volume of the soil, the dry soil only. So this is the volume we are looking for. We have the initial volume, and we had the initial volume, and now we have the final volume of the soil. So then we can use this equation 14, this one, the initial one, initial volume, and the final volume with equation 19. We can use them in this equation 13 to obtain the shrinkage limit SL. It's tough, right? Okay. Let's keep this formula here. Okay, another parameter that can be determined from the shrinkage limit is the shrinkage ratio. Have you ever heard about this? Shrinkage ratio. The shrinkage ratio is the ratio of the volume change, how the volume will change, means delta V of soil as percentage of a dry volume of the corresponding change in moisture content. The moisture content and the volume, the variation of this. This is about this formula. Okay. The final variation of the volume divided by the final volume, variation of the mass divided by the final mass, M2. And for this delta M can be obtained by using delta V and the density of the water, same from this formula. Okay, M equal density multiplied by volume. So at the end, we can obtain this very simplified formula. Okay, M2 divided by VF multiplied by density of water. That is the shrinkage ratio. Another thing is, by using this shrinkage ratio, we can show that specific gravity of soil can be obtained from the shrinkage ratio and from the shrinkage limit from this formula. You can use this formula to obtain. We can use these two parameters, the shrinkage ratio and the shrinkage limit, to obtain the specific gravity of soil by using this simple formula. Okay. Maybe if you want demonstration of this, we can do also if you need. But I think you can just keep this formula in mind. Specific gravity of soil. We can also talk about the maximum expected volumetric shrinkage, and also the linear shrinkage at any given water content. Okay, for any given water content, we can talk about what volumetric shrinkage are we expecting with this initial water content. Okay, because the initial water content, sometimes it's difficult to fix it. You will just put water randomly and check what is your initial water content. Okay, then by doing this, do you remember this this one, this shrinkage ratio? This one we talk about here, the shrinkage ratio. Okay, SR. By using this shrinkage ratio, we can obtain the volumetric shrinkage as volumetric shrinkage equal to this one, the shrinkage ratio, which multiply this, the water content minus shrinkage limit. So any water content you have, just replace it by this and minus the shrinkage limit. You will obtain the expected maximum expected volumetric shrinkage. Yes. Also, this one, the linear shrinkage is obtained by using the volumetric shrinkage with this formula. Okay. Linear shrinkage. This table is showing typical value of shrinkage limit of some clay mineral. Okay, you can read this later also if you want. Okay, so clay mineral. This is just like, I mean, from it just some gaps, some intervals. Okay, yeah, not unique value. You can read this also, use it as reference. Okay, maybe we can try just one example to see, will help you understand this deeply. The following are the result of shrinkage limit test. Initial volume when the soil is saturated, 24.6 cubic centimeter. Final volume, 15.9 centimeter. Initial mass, 44 grams. Final mass means dry state, 30.1 grams. And we are asked to determine the shrinkage limit of the soil, SL. After that, determine the shrinkage ratio of the soil, SR. And after doing that, you can then try to determine the specific gravity of the soil. And I think the last question is, if the soil is at moisture content of 28%, then you are asked to estimate the maximum volumetric shrinkage, VS, and the linear shrinkage. Okay? So maybe I will not do everything for you because this just directly apply the formula and you can obtain all of them. Okay? Maybe we'll do just one. So just the given data, let's put them here. M1, initial mass, that is here, 44. M2, 30.1. Okay, V1 is this one, 24.6. VF, 15.9. And this is no. You know this, everyone should know this. So, density of water, 1 gram per cubic centimeter. Okay, so from this, we can obtain everything we want, all of them. Okay, so I will put the formulas here, all the formula you need. These are the formula we talked about in this video. All of them are here. So by using this formula, you can answer all these questions. First, the shrinkage limit of the soil. That's the formula here. Okay, shrinkage limit, you just apply. M1 is here, M2 is here, again M2 here. Fi, the initial volume, is here. FS, FF, Vi, Vi is here, VF is here, and M2 again here, and this one, density of water, is something you should know. So directly apply it and you can get, maybe if I'm not wrong, around this value. So shrinkage limit in this case is 17.28%. That's your shrinkage limit, okay? Just remember, if you don't use this percentage, 100, you will get it. In that case, you should not put this this percent, it will be 0.1728 without this percent. But if you have 100 here, 100 here, multiply by 100, you will get this in percentage. Yeah. So if you want the shrinkage ratio, that is here. Okay. You can get delta V is just the volume, the difference, the variation of volume. You can get it easily. Delta M is variation of mass. Yeah, I think you can just use this one for simplicity to make it very simple. M2, you have M2 here. VF, it's here. And the rho W, density of water, is here. By doing that, you can obtain the shrinkage ratio very easy. I don't have to do it for you, okay? So this one, specific gravity also. If you obtain SR, the shrinkage ratio, and you already have the SL, the shrinkage limit, which is here, you can just directly apply this formula and you can obtain specific gravity. And now VS, the volumetric shrinkage, if you have SR, this one, and you have SL, shrinkage limit, just replace this water content by 28, because here it's saying if the soil is at moisture content of 28, so this means this one, 28%. Okay, by doing that, 28, in this case you will put 28 because you will have this in percentage, and this also is in percentage, this also is in percentage. Okay, if it is not in percentage, then for example, let's say here it was 0. You didn't use percentage, 0 point something, 1728. In that case, here also you will use 0.28, and the SR you will obtain, you will not use percentage also. But since right now we are talking about in terms of percentage, you have to put the 28%. Okay. And the last one, the linear shrinkage. If you have the VS, just replace it here and you can get it. Okay. So I hope you have learned something, because that is all for this video. And let's continue this program with another video. Thank you very much for your time.